All right, let me just set you up for what I'm going to be showing you. I will show you precisely what they're saying, how light appears to be going that way and this way at the same time. In these pictures right here, taken with CMOS, which is CMOS, complementary metal oxide silicates. This is a panel that shows some different interactions. This is red and red and green at the same time, coming through the same venturi, and you can see the intensity of each of them. I'll show you that. This is the interaction that causes what's called Whistler waves, which are out here. I will show you that. And this is Fermilab's particles, which are the same ones we found. Now, let's just get started. All right, I suppose this is the best place to start. This is what Fermilab posted, which is the black muon and the glowy point particle called the electron neutrino. The two of them together make up a Dirac neutrino. So they're together, and now they call them a gluon. All right. So this is what they look like here, the black and the white. In colorized version, this is them. It's exactly identical to this. Now you can see how big this is compared to that one. This one here has no mass that we can find. I'm not, literally almost nothing whatsoever. And I do have a new model I'm looking into now to explain that. But boy, I'll tell you, it's hard to explain. Because this is the stuff you put in your car and in batteries to charge them up. It has no weight. You charge up a battery, it doesn't change any weight. You discharge the battery, it doesn't change any weight. It's this thing seeking the black, pushing through the wires, glowing like crazy, and forcing the motor to drive down the street, but it doesn't have any weight. It's just a phenomenon I am hard pressed to explain. However, we know these are the two smallest particles. For CERN Fermilab, they don't disagree with that. They're the smallest particles they can find because they are the smallest particles. Although we did find one that I can show you that was a shocker. Now, these two here and these two here are just nothing more than two dipoles, back to back, and at that point they are basically stable as light. They have a big magnetic field around them, surrounding them, a big fluffy field. And when it hits something, it goes, it glows, and the other one glows too. I call it push to shove. When you push something against other particles, they glow like crazy. Now I'm going to show you precisely what they're saying is the light goes both ways at the same time, which is what this is doing. And this is it right here. And on top of that, my good friends, this is fission where the black separated from the white. And this is fusion where the black comes back to the white. And this is raw electron showers, is what you want to put in your battery to make it run your car or whatever that battery does, or plug it into your house. I think we get free energy just by doing this, just by forcing it through the venturi, keep all the black stuff back and let all the white stuff that has no mass to it whatsoever flood into your battery. Free energy. Okay, my friends, this is going to be fun. You know that I have dipole electron flood theory, which is right here. And that's what I say a proton is. It's not one big ball of positiveness and a couple tiny little floaters, which are negatives. It is a ball of dark matter in the center, literally dark matter, which creates gravity, which attracts the white matter. White matter is attached to everything. So this is a source of gravity and this is a source of dark matter. Well, what have they just come out with? Reverse time travel. Well, I can explain it quite easily. All right, this was just sent to me by my friend Stephen Bentley, and he says they're showing experimental evidence shows reverse time travel. Well, I will show you, I have also that exact same evidence, and it doesn't show anything about reverse time travel. It shows bounce. Here's what they're saying. Listen to what they have to say.
What if I told you scientists just observed negative time in quantum experiments? Sounds like science fiction, right? But it's real. Researchers at the University of Toronto discovered that photons, particles of light, can spend negative durations in their interactions with atoms. Here's what they found. When light passes through a cloud of atoms, photons are absorbed and re-emitted, but their measurements showed the photons appeared to exit before they entered. It's like seeing a car leave a tunnel a minute before it went in. This doesn't mean time travel, it's all about quantum mechanics, where particles behave probabilistically and don't follow the usual rules of time and causality. This discovery could reshape our understanding of quantum systems and even contribute to future innovations like quantum computing or ultra-secure cryptography. To learn more about this, watch our full YouTube video. See you there.
All right, look at this statement here. Just look what the statement says. Negative time observed. Scientists discovered that time can go backwards. Well, they're associating light to being time. Why would they associate light to being time? First of all. Secondarily, they can see it going backwards. The light is going backwards because it's bouncing backwards before it exits the other direction. It's only when it interacts because it bounces backwards. It's called reverse electromotive force. And I'll show it to you. I can show it to you all day long. Very, very, very simple principle. And they're making a big thing out of it, looking for funding, I am certain. Okay, my friends, they are relating photons of light to time, which they are not related. They're saying there is no definitive proof that photons, which are light, can travel back in time in traditional sense. They don't go back in time at all in any sense. They bounce. Recent quantum physics experiments have shown evidence of photons seemingly experiences negative time. It's not negative time, it's bouncing backwards, where they appear to exit a material before entering it. No, it's bouncing backwards as they hit the field of that particle. I will show you. They're saying it suggests a phenomenon that could be interpreted as a kind of temporal reversal on a quantum level. It's a bounce back. It's very simple. Often described as a quantum time flip, where a photon is split and behaves as if moving both forward and backward, which is true. It does. You see, it's very simple. The key here is it has to be interacting with something. If light is just going through the gases in there and so forth, they don't really consider that much of an interaction. It would be like this right here, where the light is coming. It's just starting to accelerate. Otherwise, it really doesn't do too much to the fields that are in front of it. These are all fields. Every particle there is has these white little particles attached to them, and they glow when they're being pushed. This is light from a pulsed red laser pushing against particles in the air. This pushes, these shove back, you get a glow. This really glows because it's coming forward. You're not going to stop it, and it's accelerating now. Yes, we can accelerate light. You can see it, very simple to accelerate light. You need to use a Venturi. Now, using the Venturi, we have extreme reversal. If they want to call it time reversal, call it whatever you want. All we did was bounce the light backwards. And I can show you light would seem to be coming back this way and going that way at the same time, which basically it is. It's because when it hit the Venturi, it literally exploded. Some squirted through, some bounced back. It's a bounce. That's what they're talking about there. All right. I'm saying they do not understand what they're seeing because they don't understand dipole electron flood theory. Every particle there is a dipole. When they become big in mass, the dark side goes to the center and all the white side, this stuff here, goes around the outside of it. So you have a black hole, basically. That's why we've never seen dark matter. It's inside of everything. It's part of light. I just showed you the black and white particles. Now, this is the particle here accelerating due to a fully understood principle called a Venturi. Anybody that's a physicist or even a hobbyist understands Venturis. The restriction is nothing more than a nozzle on a hose. And it comes in at a certain speed and it goes out like at a bazillion times faster depending on how much you pinch it. Well, we pinched it tight, and all we allowed was the white, because that can go down or big. It doesn't matter. The black is one size. Bam, bam, bam. I can't get through. Too bad. Get out of the way. It slaps that white through. But in the meantime, it blows back this way. Now, here's what I want you to look at. You see these lines back here? I'm going to focus in on that. You see those lines? That's called reverse electromotive force. Why are we seeing these lines back this direction? You see them going this direction? It should be going in the direction of the wave. Well, the wave is getting bashed back at because it's hitting here, and right about here it says I can't get through that slit. I'm hitting some atom, like they say when it interacts with other atoms. Well, it's the same thing as here. It's interacting with an atom, which is basically the here, and it bounces back. It's just a reverse bounce of light. It's basically light. Now the cool thing about this is that all these light particles here are coming through there, and they are particles that are black and white, back to back, side by side, two gluons. You call them whatever you want. They're dipoles, dipole electron flood, and they're coming here. You don't see them, but they're all over the place because they're spinning, coming forward. The only reason we see these glowing here is because of the reverse EMF, reverse electromotive force. And it's going back this way because it can't get through. It's just bam, bam, bam. And they're hitting here so hard that these things light up like Christmas trees right here. All around it, anywhere where there's one of these waves, they light up like crazy because the wave is there. You just don't know it's here. This wave is here. It's all the way back here. This wave is all the way back here. Same thing here, same thing here. But until it gets smacked back hard enough, it doesn't illuminate. And once it illuminates at the tip, the glow is gone. You know what they say, the glow only lasts so long. Now, this is nothing more than the black particles just can't get through. And so what happens is the white ones so desperately want to be attached to the black, they suck them all back in here and they come out through as Higgs fields. And the crazy thing is, these are nothing more than Higgs fields going in. So you got Higgs fields going in, being crushed and coming out as Higgs fields. Let me show you. But here they separate. So we see them coming out as particles where there's nothing. And then Higgs fields show up right here. All right, so here's the progression. The light is pulsing through here, and it's just now beginning to accelerate. Otherwise, you wouldn't see this at all. You would not even see it whatsoever. And there's a whole bunch of them coming forward, but this one here is right dead in line with the Venturi. So it's beginning to accelerate. As it does, it excites all the molecules in front of it. It's like pushing through it. It's like slapping it out of the way. So now here it's starting to accelerate. And it will accelerate right now because the particle is there. And here is the acceleration. The particle that was there is now being sucked directly out of the wave. It's so energetic now. All right, so what is energy? Energy is increase in energy means we should be able to get more energy than we had here. That means free energy. So we're shooting this thing in at, say, 5 watts worth of energy. As it's going here, it's creating enough to light up the room. So let's say it's 10 watts. I don't know, whatever. But that is the particle accelerating. Here is where we get in that reverse EMF, creating what they're calling reverse time. It's not. It's just bouncing back. Here's the cool thing. Because this is fission, right here, black separates from the white, and this is fusion where it comes back together. This is looking into the Venturi. So we're looking into this way right here. We're looking in. And coming out at us is Higgs fields. Here there's nothing but white. You see here, there's nothing but white. So we got nothing here. There's just nothing but whiteness. And then all of a sudden, exactly here, the same thing. They start slamming into these Higgs fields. And I mean they slam. All right, so that's the progression. We go from just barely getting started to accelerate into full acceleration mode, where you get the fission and fusion right here at the Venturi, because only the white is allowed to get through, because only the white can get small enough. I know I showed you this, but let's look at it one more time to be sure that you understand. They know these are the smallest particles. That's directly from Don Lincoln's article at Fermilab. Now, this is over 10 years ago, and I contacted him. I said, Don, we found your particles, and I am blocked from Fermilab. They won't let me communicate with them. And I haven't been able to for this entire time, over 10 years. We found these particles, and I said, you're right, this one glows, and let me put this back up. That one glows, the white one, and it can get big and it can get small. You can see it. Here it is. And he said the black one has a glowy edge around it, never changes size. I agree with that. They're all the same size and they never get smaller. They shield this one. The light is going this way. If you could see it, all these little particles in front of the glowy one are the ones that are glowing, pushing back at that particle. This one's being shielded by the black. It's right in front of it. So this one starts to get zzz, and this one goes zzz. Now, then it flips. And this one comes in the front and this one goes in the back, and you start to absorb more energy. Now, again, let's look at this in detail. This is earth-shattering physics. This is over the top, changes the atomic model. Everything changes with this, and we might be able to get free energy. All we want is the white part. That's all you want. As long as you can get that white away from the black, that's free energy. You see this? This is what CERN and the Large Hadron Collider, Fermilab, Lawrence Livermore, they all want to create these electron showers and keep the muons back. We did that. What we need to do is right after the Venturi, before the white rebonds with the black, we need to feed it down through a photodiode and use that energy for whatever, batteries, run whatever you want. We should be able to get 200 times more energy than we put into it. Maybe not. All we need to do is figure it out. Yep. Okay, a little interruption there, but if we could do this, you could put literally thousands of these little devices inside a little box like that. It's a little Geiger counter, but like a lunch box. You carry that around and have all the energy you would need. If I'm right, if it gives you this kind of energy increase, which that's what they're saying. All right, what I want somebody to tell me is if I'm wrong. They're using protons. They make these big collisions. They get a whole bunch of what they call hadrons and so forth. They have to decay, and then they get the neutrinos. And then the neutrinos create the two different flavors, the black and the white, basically, the electrons and muons. Now, the energy of the neutrinos in this device that they use to separate them, the energy of these neutrinos can go from a few hundred billion electron volts to a few trillion electron volts. Normally, you would be starting out in the very high mega electron volts, millions of electron volts, but not billions, I don't think. So you're going to have a very large increase in energy if you can pull the neutrinos apart. And you can, from the electron neutrino, from the muon neutrino. We did it through the Venturi. It cost us nothing. We had to add no additional energy, and it's portable. You know, I think I just noticed something I hadn't noticed before. I've always said that the photons will always stay straight up and down with the Earth. They call it upspin and downspin. That's an upspin where the top is going forward. That's a downspin because it's the energetic part is down. Now, they never go like this. They never go like that. Even when they're not to full energy. Look, you see these here? Straight up and down, sideways this way, straight up and down. All of those energy interactions are polarized towards the Earth in one way or another. These are flat polarized, some of them. Like, see these here? They're flat polarized until they gain enough energy to become straight up and down polarized, and then they show up right in the Venturi line as photons. And then they bounce back. So they see them going both ways. But they will never go sideways. They'll always be exactly straight up and down. And I can prove that showing you with the green. The green will be going sideways, but the particle is always straight up and down, even though the green line is going this way. There it is right here, see? There's the same, straight up and down, straight up and down, straight up and down. And this one's straight up and down. They don't, even though it's going that direction, the particle's not spinning this way, it's spinning this way, even though it's like spinning up as it goes. Now there's only one exception I have found to this, is when a guy named Fabien Brulé did both Venturi, one Venturi and both the red and the green, and here it is right here. This is both particles same time through the same Venturi. And what happened is they were close enough together, this one here the red, and this one here the green. All right, and they were close enough together that the red's field opened up like this when it came through, and so did the green, but the green is much more powerful. So as it came out the other side, it wanted to open up like this, but the red was sort of opening up it this way, but it just said, get the hell out of the way. and it reconcussed way out here. Now the red just doesn't have that kind of energy. So what happened was the green came past the red particles, which are spinning this way as they're supposed to be. And the green is also doing the same thing, but it's going real fast. And when it hit this field, it started spinning them this way. That's a barrel roll. They don't do that. That's just not, it doesn't happen. The green forced the red to barrel roll. Now, I have never seen that any other time than this. But I've never seen them both coming through the Venturi at the same time either. Now, do they interact that way in the air? I don't think so. I have never seen it before. There's a lot to look at this here, but that obviously is the particle we've been looking at. That's the photon. Now, some of the pictures come out just stunningly fabulous. Stunningly magnificent light bulb. Here's that green. There's the dark particles, there's the white particle. Now they're held in there just as tight as can be. You cannot pull that apart. This is what generation of electricity is ripping the white away from the black. And then the white goes into a battery or whatever. It doesn't have any weight whatsoever. The black, you got to rip off and keep behind. I never knew they could separate. I had no clue about this until I realized, and I saw an atomic bomb blast go off, and the white goes first because it coats the black. The white goes first, and the house just sizzles like this and just smokes, doesn't move at all. And then the black comes, and so the black has all the weight, no weight, and all the energy. Crazy, but that's the case. All right, let's start summing things up. Reverse electromotive force. There it is right there. Those fields are bouncing back this way. So they think the light is going backwards in time. That's insane. It's hitting here and bouncing backwards. Simple as that. Now this is fission, where the black separates from the white. The white is all by itself. If we can harvest it right there, that's what I was talking about. Send it right down before it gets back to the black. But right now it's reattaching to the black. And at that point it's too late. It's already become back to atomic vapor. You see this right here? That right there is the muon neutrino. That's the black ball. It never changes size. However, the white ball, the electron neutrino, can get all this radiation causes a shower. As you saw, that white everywhere. This one, when this hits the heavy water, this one goes on its own, and that goes into a shower. Precisely what we did. All right, precisely what we did. Identical. All right, this is just like hitting heavy water here. The black goes on its own way. The white is the only part that can get through. The Venturi is not big enough for the black to get through. And it keeps slapping the white, so the white has no option other than to squirt through. It's being forced. If you can harvest this somehow right here in that little bucket and send that white down, into whatever you want to use it for, and then bring it back to the black. But right now, it's rejoining the black right here. And you see right there, that is the distance of entanglement. They talk about entanglement with the black and the white. That's entangled quantum photons. Now, the green is going to be entangled way out to here. It depends on how fast the particle is spinning. And they spin, they don't flap like a wave. They spin. I can prove that too. But you see these black particles? They're all exactly the same size. Every single one of them. The green, the black, the blue, the red, they're all the same size. And there's nothing more than these black wants to do is to be attached to that white. Or actually, the white wants to be attached to the black. There's got to be all these blacks floating around. And this idea of quantum entanglement and go light years away and still be attached, absolutely ridiculous. Right here, they break apart from the entangled state, and these are not grabbing these, jumping over here, and no, I don't believe that at all. I believe there's just so much extra dark matter, literally dark matter. And everything there is made out of dark matter. They say that we can't find it. All we can find is the very small amount of matter that's in the universe. Well, what do you think you're standing on? You're standing on dark matter. The problem is they never realized it because they don't understand dipole electron flood theory, that the dark matter is inside the glowy stuff. So every time you look at this, all you can see is a glow. If you could get inside, that's where the dark matter is. All right, but it's normally like this. It's all like that. So you look at it, you look at it, oh, I don't see any dark matter. All I see is a goose, or all I see is a no-toe, or all I see is whatever you're looking at, a feather. No, but inside of you can't see the particles of light because they're inside. Everything's made of these two particles. That's dipole electron flood theory. There's not a single thing that isn't made of the black and white particles. They're just in bigger and bigger and bigger stable quantities. They call them atomic masses. And hydrogen is not one big proton and one tiny little electron. It is approximately 1840 or so dipoles in a ball like this. And what happens is the black particles are pushed to the center. All right, so they're surrounded by those white particles. All right, so the black is in the center, the white particles are on the outside. And this is the smallest possible configuration of particles that's stable, hydrogen 1. Now guess what happens? You ever see what happens when you put a spark to hydrogen? The explosion is phenomenal. Because hydrogen can't get any smaller. So when you spark it and you start to blow off some of this stuff, everything goes at once and boom! And you get an explosion like, basically it's the tiniest atomic bomb, because all of these particles that go out and then the black follows it. And when you hear the kind of a explosion it makes, it is deafening. And I mean seriously, you can get deaf from it. All right, so I'm going to show you, this guy's going to set off some balloons with different gases in them, and they're explosive gases. And then he's going to do the hydrogen, which is the real exploder. Now, I say hydrogen is made of about 1,840 of these little dipoles. They're just little more bar magnets, and they're stuck together real well at about 1840. But if you bring a match or a spark or anything in here which causes a disruption in that layer, the whole thing goes at once, and I mean it is unbelievable, because every one of these little bar magnets comes on its own, and when it does, it gets a field like this instead of a field like that. When they're all tight together, their fields are intertwined, and they're what they call gluons. But when they go on their own, the field gets huge. That's why you get this absolute unbelievable explosion. Wait till you hear what happens when he sets that puppy off. These kids, and this is the way a teacher should teach. Now this is Alex Smith, all right, and he's got this hydrogen oxygen balloon explosion 11 years ago. All right, get ready. All right, check this out. This is fabulous. As I said, I mean, hydrogen is the smallest particle that's stable. And it goes up instead of down because it doesn't have enough mass to be pulled to the earth, so it sort of floats up. That's why hydrogen balloons go up in the air. However, if you put a spark to hydrogen, instead of it breaking apart like in a half, it explodes and every single piece goes on its own. And I mean, each one of them takes up a big field. And you can see this in what's called an electroscope, where you discharge electricity into this vacuum chamber with all these foil plates, and they're sticking straight down. And when you discharge it, the electrons come down and it goes bloop, all these things stay, and they stay apart because they're in a vacuum chamber. The electrons can't get away. So the fields are like this in each one of them now. There's extra electrons, and that's why they got all this from that spark. You come up and discharge that, and they just go bloop, they drop right back down. So you're putting electrons in, and you're taking electrons out. That's what an electroscope is. Okay, this guy's got an electroscope, but it's not the type that's in a vacuum. So he's going to just bring a charge up towards it, and you'll see the gold foil will open up. Here's what he's going to do.
It's got a piece of metal up here, and that's connected down to a metal piece with a piece of gold leaf. And when I bring a charged particle to it, you can see
all he's doing is bringing this metal comes down and it's attached to this pole. When he brings electrons over and they push down in here, as they're feeding into here, it pushes that away. The harder the charge, the more it goes like this.
That the gold leaf moves. Now, why is this? Well, when we bring something charged here, it's going down this piece of metal, onto this piece of metal, and onto this piece of gold leaf.
What it's really doing, I'll cut it off at this, he's bringing over extra electrons which are discharging into this ground. It's accepting them. And as they fill up in here, their fields, they're like little balloons. They push the little balloons that are on the gold foil away. It's got to be very thin, and it pushes it away like this. It depends on how strong the charge is. Now, they have other electroscopes that they're vacuum chamber, and they have a whole batch of little foils in there. And then you come over, and it's got a ball up here, and you take static, like you charge up a little something, you go snap, and they just go, and they stay out there. They don't come back. This guy has to go here, and it will always come back because he's not in a vacuum chamber. And the electrons can leak out. Here in the vacuum chamber, they charge up and they stay charged. And all of these balls are in there, of little electric field balls, basically, is what they are. And that's why they separate it out like this. You come up and you discharge it, and they go snap. They drop right down to nothing. Very cool. I want to go back to all the old experiments, because this is how I learned how, how does electricity conduct through all these different mediums. Liquids, gases, vacuums, conductors. What creates a good conductor versus a bad conductor? What affects conduction when heat is involved? All of this stuff I understand extremely well. I've dealt with this my whole life. I fully understand it. And if anybody wants to say, Roger, you don't understand it, here's what you're doing wrong, well, let's talk. But I'd like to have somebody that has some background in it that can point to something material other than something, oh, no, it's got to be some mystical thing. I go for science. I know what's going on there. These fields are coming down and they're just opening up like a balloon. So that particle, instead of staying small and round and little white particles, they just bloop, and they never come back out. And it depends on how hard you hit that thing with static, how many extra charges go in there. Okay, this is where the chemistry comes in a little bit. It's not any big deal. Like I said, when we're down at the very smallest particle there is, when it breaks into every particle, and it gets to the explosion. It's just knock your socks off. What this guy's going to do, this is Alex Smith, and he's going to pop these balloons with different gases in them, which don't have a ton of energy. They're just not real explosive gases. And then he's going to do hydrogen, which is very explosive. Now, I'm going to play it, and listen to what he has to say here. I got the closed captions on. Let me turn it up the sound here. Here goes.
I never ignited 4 balloons at once. Let's see what happens. And what you feel here in the first row, this is the...
All right, you see, he's showing some kind of formulas here. I don't know what he's doing with these, but they're not the kind of combustion that you're going to see with the hydrogen. Now, what he's going to be doing is popping these, and they make a good pop, and then he's going to do the hydrogen. Now, what will happen is hydrogen is mixed with the oxygen. I believe he's going to have hydrogen and oxygen gases in the same balloon. And when he explodes, it just goes all off the charts. And there's something to do with oxygen, that the more oxygen you have, the more reaction you create, the more explosion, the more violent flames and everything. Oxygen makes everything work, even in us. So here he goes. All right, no big deal. Nobody's going crazy. Let's see what happens now.
Remember that sound, how it sounded, and compare to the sound you will hear.
Now, what he's got, apparently he's using H2 plus O2, hydrogen and oxygen together, and after it explodes, the extra oxygen turns into literally dipoles. He's got a changing hydrogen and oxygen, whatever. But the extra oxygen, it turns into, it started with H2 and O2, so they're even. It explodes. What happens? You get water, and you're going to see water vapor in air. That's H2O. See, H2O. You end up with 2 of those. And then what happens to the other oxygen? All right, the other oxygen turns into bits and pieces. All right, because you first started with H2O, 2. So now we got H2 and only 1 O. The other O turned into bits and pieces of explosion, along with the hydrogen. It's loud. Get ready, because it totally destroys itself.
If that sound was too loud for you, keep your mouth open, because then the pressure in your mouth
Oh yeah, oh yeah. Yes indeed. Now you see that? That's not just smoke. That's water vapor. Kids are loving it. That's the kind, look at it, these packed house. They're standing in the back. This is the kind of science teacher you need. Good job, my friend. Okay, the main theme of this whole thing was light being seen going backwards and forwards at the same time when it interacts with matter. That's the key. This is matter. It's going backwards and it's going forwards at the same time. Very, very, very simple. So what have I showed you today? Muons and electron neutrino together, which is a Dirac neutrino. When they concuss, they split, and the muon goes sterile, they call it, all by itself, and the electron goes into the shower mode. That's exactly what I showed you. I also showed you fission, which is the black separated from the white. I showed you raw energy, which has no weight to speak of, and then fusion back here. The black separates from the white, the black rejoins the white. I showed you duration of entanglement. This is completely new physics. In the last 10 to 20 seconds, you just heard it.